Hello everyone, I'm Ruaridh Macdonald. I'm a research scientist at the Energy Initiative, which is over in E19 towards Kendal. We're a group that kind of sits in between the different schools and works on, we have a cadre of maybe 4 or 5 research scientists now. We each run our own research groups, and then we also work together with the faculty and other researchers around the Institute on a variety of policy, technology, and assessment, all sorts of energy-related work. As part of that, we developed quite a few, no, give a little overview of myself. So I did my PhD here in nuclear engineering, and in an effort to kind of work out what to do with nuclear reactors and how to design them better, I got into this grid modeling space, and gradually that's expanded to what I would call multi-sector modeling. And our work typically goes through these cycles of, we have a lot of interesting applied questions, we run into some modeling roadblock, we spend some time improving the modeling capabilities, and then we go back to the applied work. And we probably do about 2/3 applied, 1/3 methods on average. And as part of our work, we've developed a suite of modeling tools. So we have some that are very focused on detailed facility level design, particularly looking at what are all the nonlinear details of these co-production facilities or facilities where you don't mind the fact that its actions or investments might not affect the rest of the grid or the energy system. Infrastructure planning tools where you do make that connection and you have feedbacks between all these different systems. But those models are optimization based. And then increasingly, or in the last year, we've been looking at simulation models where instead of assuming that we're going to set constraints on outcomes and optimize our way to those outcomes, we're essentially going to define different companies and agents in the system, and given their preferences and predictions of the future, see how the system evolves forward in time. I'm going to focus on the middle category today, and in particular macro, which is the most recent model we've been using and is currently used by people, a good number of people around the world now. So this is kind of an ongoing process of us learning how best to teach the code. And so please, if you have questions, feel free to pause me and ask them. So as a quick, just because I'm not 100% sure what we've all covered with the lectures, wanted to make sure we're all on the same page with what are these infrastructure planning models trying to do. So we'll have some very high resolution data set for what our grid looks like, or natural gas pipelines, or data center network, or what have you. And given the computational feasibility or kind of amount of time we're willing to spend on a problem, we're going to aggregate some of that. So typically we might aggregate the distribution network to a transmission level model. And for each of these aggregated zones, we're going to work out what are the commodities of interest and what are their hourly or 5-minute or 4-hour or daily, whatever time resolution you want, you find the data for the demand for that system. So most of these, I'll come into this in a second, but all the models I'm talking about today are demand side only. They're not they're supply side only. They're not supply and demand. So we have exogenous demand at each, in this case, 4 nodes, and we put in a big list of technologies that are available. So here I focused on electricity technologies. We have wind, batteries, fission, a couple types of natural gas generators, a couple types of renewables, and then transmission. And each of those are parameterized by a set of costs, a set of technical capabilities. And on top of this whole thing for the whole system, we'll say what are the public policies or policy goals or reserve requirements or anything else that you might have at a system level. And this all gets baked down into a linear or nonlinear or mixed integer program. And the optimization model essentially says, okay, where should you invest or where should you build all of these different resources? And what is the high level outcomes for the system? And then zooming in on each zone, it'll tell you how should each of those things be operated at the resolution of the demand input data. So there are a couple of assumptions here. One is that we can tell it that there are existing resources, but these are optimization models, so it doesn't really have a sense of time in between them. These resources all appear on the grid, and then they operate for some representative operating period, which might be decades of data, but the implicit assumption is that after we get to the end of this time series, the model comes back to time 1. It's this kind of infinitely looping equilibrium. That might be decades, but it's still an equilibrium. And you can string several of these together, but unless you're very careful, several of these optimizations together, in order to get a sense for a timeline where the investments made in period 1 carry over for free, so to speak, to period 2, but under the hood, these are still kind of linked equilibria. They're not true transients, and you're not truly looking at how the system's evolving, which is a big caveat. Any questions about this, though? Because I think without this solid in your mind, it might be a bit, what comes later might be a bit confusing. Everyone comfortable?
Just for clarity, we only talk about expansion, right? We don't think about what you already have.
You can have what you already have, because you can have existing resources, which will typically be thought of as some kind of free resource to build, but you have to pay to keep operating them. So you might have to pay your fixed operation and maintenance and all your variable and fuel operation and maintenance costs. But you'd imagine that the initial investment is sunk, so you don't consider that in the optimization. Or maybe there's some hangover of the loan. But yeah, you can frame it that way. And similarly, with existing resources, we'll often think about retrofitting. So if there's a coal fleet, one option is to retire units, the other option is to install CCS of some sort, or retrofit it to be a higher temperature or something like that. Any other questions? Okay. Well, and to continue to kind of frame where these sit in this catalog of different models, if we were to look at, oh, I forgot one label. If on the far left is kind of millisecond operations or a couple seconds of operations for how you're actually going to dispatch your grid, those are typically power flow models. So you can't build something in the next 5 milliseconds or 5 minutes. It's really all about operating the system. And you have very detailed models, tens of thousands of buses. There'll be at least DC OPF, if not AC power flow and AC physics considered. And there'll typically be, there'll be supply side only with maybe some small demand variability, demand side operation. And on the other side, you have supply and demand models, an example of which would be integrated assessment models. And they have essentially solved to an equilibrium where they have a set of demands that they anticipate happening in the future. They calculate what they think is the optimal supply for that. That's going to change the prices of all the commodities. Let's say if more renewables come into the grid, then the emissions intensity of concrete might fall. So then you can use more concrete while still making the same total amount of emissions, and you get those feedbacks between supply and demand. But the flip side of that is you typically have low resolutions. Like the whole of the US might be one bus, so to speak, in that system. And capacity expansion models live somewhere in the middle, where they're medium grid, medium detail, supply side only. But as research is continuing, I think they are becoming able both to integrate with these other two models, and so kind of borrow higher resolution there and borrow some of these feedbacks, or they are just more computationally capable, and so they're able to do more themselves. And what do you use these things for? So this is an example from a paper from the CEPA group, so over in Sloan. Juan Senga, who I think is talking tomorrow? Juan? Yeah. Juan's, yeah, talking tomorrow. I think not on this work, though, but he essentially ran several of the scenarios of the US to see, under different transmission build-out scenarios and different policy scenarios, what might the optimal grid mix look like in order to meet certain affordability and decarbonization goals. And as a function of these different scenarios, the system told it, the GenX, in this case, the capacity expansion model, told him how the non-served load, for example, would vary under different stochastic inputs and given these different transmission build-out scenarios. So you can study policy choices and decide, all right, how should we fine-tune the details of that transmission investment policy or transmission investment plan in order to get the outcomes we want in the rest of the system. Similarly, you could also use them to optimize or pick an R&D path forward for new technologies. So this is a study that we've done for some of the thermal storage technology under development in the MECI department here, where they have a couple different levers they were trying to optimize. One of which was the temperature range their thermal storage would operate in. Second was how much installation they should pay for. So essentially, the less the thermal leakage of the system, the more it would cost. And then what should the charge-discharge storage ratios be? And we found that the answers for these, here we have some examples where we essentially found it should be as hot as possible, and there was an optimal loss of about 3% per day. And the charge-discharge ratios varied a lot depending on the market you're in. Were you in a solar dominant market? Were you in a wind dominant market? Were you in a place with summer peaking or winter peaking? And so this sort of, it didn't tell them how much it would cost to achieve any of these R&D goals, but it told them what different markets would be willing to pay for those capabilities. And then they internally can say, all right, we think that improving the insulation will cost us $1 million of effort in the next 5 years, but the payoff is much higher than, say, increasing the temperature further. And so macro is one of these capacity expansion models, one that we developed recently here, and its big focus is on being a multi-sector capacity expansion model. So as time is going on, more and more systems are getting electrified, renewable electricity is very cheap when it is cheap, and storage is becoming cheaper and able to spread its spread the kind of cheap renewable hours over longer periods. So there's also more electrification in the grid, and that means that renewable variability is beginning to impact other sectors. And so we're very interested to understand how we should optimize those systems to insulate some part of the systems, reduce the total system costs, achieve decarbonization or affordability goals. And we've begun to use it for several projects with collaborators around the world. So there's projects ongoing in the US, South Korea, India, China, Brazil, a couple in Europe. This is a map. We have some online tools, which I'll show you at the end, and this is the map of where people in the world are accessing them. So it's a little washed out by the US, which I think this is on number of people pinging the server. So it's a couple hundred in the last week, whereas Germany had quite a few, Sweden, the Brazil group, a couple in Australia recently. And the model really has a focus on scaling up as much as possible, partially so you could run very high resolution systems. You might begin to get into those hundreds or even thousands of buses that a power flow model has. But there's recent studies that show that for these capacity expansion models to give accurate or robust results, they have to consider at least a decade, if not decades, of data to get a good impression of how do particularly renewables availability and demand correlate with one another. And so we want to have decades of data. We want to be able to have a relatively high resolution grid. And that's been the focus for macros, is facilitating that. Kind of side effect has been that if you're okay having a slightly smaller electricity grid, you can add in a natural gas grid or a hydrogen grid or a data center network or whatever you want. It's very flexible, which I'll get to in a second, but we have several kind of sector models built in. And this is a list of the main ones right now. I think it's already a bit out of date because the collaborators generally have sectors they're interested in, and as they're working on them, they're just adding them to the system. Now, a little bit of, why did we build macro? So recently I discovered that there's been about 20 models published a year, which I think we'd all agree is a lot. It's probably, roughly 20 times too many. This is combining different types of models: capacity expansion flow, power flow, production cost. But we were trying to understand, why is this happening? Is this because there's some really good reason for doing this? Are the models not general enough? And we kind of were inspired a little bit. I don't know if people still read XKCD, but this whole idea of, we were worried that if we're going to build this new model to solve all the model's problems, are we just kind of piling on more here? But the three main reasons we ended up deciding to move forward were, one, a lot of the models had been designed to solve what I'd say like a policy or technical problems. They hadn't, from the very first step, thought about computational scalability and made sure that all the architecture decisions they made along the way made it easy to scale these models up. And so that was the first priority. The second one was, most of these systems were electricity first. So they built a grid model. Everything was coded with electricity in mind or structured with electricity in mind. And then they kind of would copy-paste sectors. And we did this in the past as well. Copy-paste sector models, Control-C, Control-V for everything electricity related, and just rename it hydrogen, let's say, or rename it natural gas. And that made it very hard to keep on adding more things to the model. You essentially had to pry apart the whole thing anytime you wanted to add something unique. And that meant that things that were pretty simple from an architecture point of view were taking months. And so we've tried to make this as simple as possible. And now I kind of get into how you all might use macro. So in order to make it easy to build with and to make it very flexible, we have kind of three users in mind. I'd say most of you are either going to be users or modelers, where your real focus is modeling something in real life, doing analysis. Ideally, we'd like you to have little or no coding required. It should be as drag and drop as possible and just inputting some data. If there are some new technologies you want to consider or new constraints or policy designs, then you might have to do a little bit of coding, but we're trying to keep it as you won't have to be very aware of the underlying structures in the system. And if you wanted to add something really complicated, or such as, let's say, a new solving algorithm, then you'll have to dig into the depths of macro. But right now, most of the other codes that we've used, kind of all these tasks are blended. If you want to create a new model, you might get away with no coding, but most of the time you're going to have to be have a very good understanding of the whole system to move forward, which just takes months to get your head around even the simplest model. So what does macro consider? It has three main components: commodities, assets, and locations. Commodities can be the simple things like electricity or flows of iron or steel or ammonia, or they can be more abstract things like compute, data. You could even do like populations and things like that. Assets are then real-world systems that create, consume, move around, do things with those commodities. And locations are the places that those things happen. So very simple structure. The key thing, though, is that all of these things have been coded these assets and locations in a commodity-agnostic way. So adding your own elements to the system is very straightforward. And in the next bits, kind of to give you a structure of what I'm going to go over, I'm going to talk through some examples of how people have used macro before in an effort to kind of help give you some ideas for how you might use it in your own projects. I'll then go through some simple examples and we'll walk through it together. In the past, when I've tried to do these workshops, we need kind of 3 or 4 hours for people to dig in and do it themselves and run it themselves, just because many people don't use Julia, which is what this is written in, so you've got to set all that up. So instead, I'm going to walk through some examples just with me on the screen, and I would ask you to, I'd invite you to ask any questions you have, and then I'll send some links to workbooks where you can go through them in your own time, because as I said, if we don't have like 3 or 4 hours, I think that's been the best way forward. But as I go, please interrupt, and especially if you have your own ideas in mind of how you might use these tools. So to give an example of a recent study, I wanted to highlight this one by Junwen Law and Darek Marla-Pagada. So Darek's now a professor at NYU. Junwen's one of the Chemie PhD students here. And they wanted to study essentially how the Manhattan electricity system might evolve in the next, or between now and 2050, with or without biogas, consumer electrification, and one more variable that I'm forgetting off the top of my head now. And in order to do that, they initially thought they could use an existing system just to model Manhattan, but they realized there were going to be feedbacks between how the rest of the New York ISO or New York grid worked and optimized. And let's say if biogas was available for Manhattan, it wouldn't make sense to assume it wasn't available for New York ISO. So using macro, they built this 2-level system where they have a bulk grid and the 12 transmission zones. And they essentially built different assets. So for this District 1 location, they had these different assets that allowed you to supply steam, 4 types of heat, natural gas, and electricity to consumers. And you had an equivalent system up top. So the bulk system had electricity and natural gas, supply and demand. The 12 distribution grids had those and steam and the 4 types of heat. And so you got these hourly demand profiles that look like we have in the bottom there. But from macro's point of view, these were just 20 locations. It didn't really mind about the different scales or even different time scales. And when you're building models, you can happily mix these different things. And so you can have parts of the model that maybe runs with, let's say, AC power flow, parts of them that are abstracted to be transmission level or just a transport model. And what he did was he went through this and he ran what we would call a case. So each of those, that snapshot of the system is what we call a system in macro. And you can chain many of these together, and macro will automatically handle the data shuffling. So if we were to have our multi-period model, as they had here, every set of investments, they started in 2020, and then every 10 years they had an investment, and they carried forward, macro automatically carries forward the investments. You could also use this to do sensitivity studies automatically. You can use it to do decomposed models, which I'll demonstrate in a second. The main strength of decomposed models is that you essentially it will automatically break your problem into little pieces. You tell it how many. So if I was going to take this off my laptop or a desktop and put it on a cluster, I could tell it, I have 30 worker nodes, each with 48 processors. Let's split this problem into 300 pieces and run it, and it will automatically handle the dicing up and the kind of management of that process. So Junwen did this, and it was able to see the interactions between those two levels of grid. So when biogas was available, it allowed for some negative emissions, which meant slower natural gas retirements, which generally meant the grid was a bit cheaper because you also didn't have offshore wind. And this interacted then with the Manhattan grid. And so on the left-hand side, you see with no biogas, you have heavy electrification throughout the system. And that was more, Macro was able to tell them where those build-ups would be. If you didn't have biogas, you saw much less expansion in the electrification system because the existing natural gas infrastructure was used for biogas. And so instead of getting rid of 1,000 megawatt miles of natural gas pipeline, you only got rid of 60. And that, you could reduce the pace and scale of investments to hit your 85% emission goal, and they were able to see that this was great. And this one I don't want to go through just because of the amount of time, but this was looking at different assumptions about the ways that people chose to electrify or not electrify their end use. I've run through this quite quickly, but I don't know, any questions about how you might use this in your own work or inklings?
Can we go back to the last slide, the one that
this
one?
So these are two types of demand. Commercial end use in the top row, residential end use here, no biogas with biogas.
This is showing the output of the model.
Yeah, this is the supply mix as a function of as a percentage. So we're saying in that first residential case, gradually people are switching to electric boilers and heat pumps when there's no biogas. And in the with biogas case, there's some people who use, essentially the heat pumps disappear. Some people still use boilers, but the vast majority use a gas furnace that's now powered primarily by biogas or a biogas natural gas blend.
How do you decide, how do you model actually the customer's behavior?
So in this case, it would be least cost optimization. So no customer is modeled independently. We have the whole network, both levels of network are being optimized simultaneously. So to say, how do you minimize the average cost for all consumers? You could put in some constraints on the model to say, I want to avoid some people one of the parts of the grid paying a lot more, and everyone else, so you have some kind of L1, L2, some kind of measure of inequality across the system. But by default, it just looks at the average over everyone. So it's possible that there's big discrepancies in how it ends up. Yeah. Any other questions about this or how you might begin to think about using it? Okay. So we're going to start getting into how these things work under the hood a little bit, and then I'll show you some examples and point you towards the workbook. So I said before that we have three kind of modeling components: the commodities, assets, and locations. Under the hood, the assets and locations are actually kind of secondary or composite components. They themselves are made up of four things. So the first are nodes, and this is essentially a component that balances one commodity and allows for external supply or demand. So if you were to have your end-use consumers, your end-use consumers are essentially a collection of nodes for their demands, and you would have some amount of heat or steam or electricity coming in and just disappearing. So going into that node, that sink, so to speak, and disappearing. Transformations don't allow for that that external connection, but they balance different commodities. So in this example, I have natural gas coming in, some process happens, so in this case, probably steam methane reforming, and you get CO2 and hydrogen coming out. Lastly, we have the storage components, which are like a node, but instead of allowing for external connections, they have a storage capacity. So they have to be balanced over time, but in any given time step, they can hold on to commodities. And lastly, we have edges, which are allow flows of one commodity. So each of these arrows is essentially an edge, and they can be one-way or two-way. And one important thing to think about is often people will look at this and say, oh, this transformation, that's the SMR process. But again, in architecting this, we realized that it was, for us, a lot better to have the capacities. So let's say the amount of natural gas that the system can take in, that SMR system can take in, is encoded on the edge. So this edge tells you how much natural gas it can carry, and this tells you how much hydrogen it can carry and how much CO2. The transformation itself doesn't have any concept of capacities, it's just balancing things. And so that means when you're thinking of these assets, like all four of these components make up the steam methane reforming. It's not like there's a supply network, a hydrogen distribution system, some CO2 capture or emissions, and then the transformation is the SMR system. All four of them together are, oh, sorry, and I've jumped ahead here. All four of them are the asset. And I'll show you briefly in a second how you can code these up yourself. There is a code way of doing it, or there's a graphical interface to pull these things together. And you define your own structure and essentially drop them into your model as part of your inputs, and it allows you to run. Locations are a collection of nodes. So it used to be the case that if I had that New York model, and I had District 1 that required electricity and steam and the 4 different types of heat, I'd have to have 6 nodes individually labeled, having to keep track of them, one for each of those 6 commodities. But locations allow us to abstract that. We can say there's District 1, and if I ever connect something that needs or supplies a commodity, under the hood macro will automatically generate those nodes for me. So it's a way of abstracting it. So if that SMR system, steam methane reforming system we had in the previous slide, was connected to a Boston location, then macro would know under the hood that it needs some supply of electricity and natural gas, and it needs somewhere to put the hydrogen and CO2 afterwards. Any questions about these?
You showed that four or five here. So can the user define something more than this if they want to?
They certainly could. That would be one of those developer tasks where you'd have to dig into the source code. I think we have yet to find something that can't be solved with these 4, including some very complicated systems where you have we can try some out. But if you have something in mind that you think wouldn't work, we can use the interface and see if we can or can't make it. Any other questions? Okay. So to give an idea of what this system looked like, here we abstracted some of these different assets at the districts, but under the hood, these are different nodes, and here we have some squares instead of hexagons, like I had in the previous slide, but essentially different transformations that are going between these nodes and carrying commodities between them. And this was encoded in a way that I'll show in a second. And on each of those components, we then have a library of constraints, and this is definitely something you can add to. You have to be a little bit careful to make sure you follow the kind of recipe for it, but you can add constraints to your system. That might be a CO2 constraint or rules about reserves on assets and components. And again, I'll show you in a second how you might do this. I think one of the most powerful things built into macro right now is the commodity system. So it starts where we have encoded a bunch of commodities which we think are useful for many systems, but you can very easily add your own. And importantly, you can also add sub-commodities and you can create this whole tree of different commodities. And the way to think about these are that, let's say we had a node that was kind of taking in several supplies of hydrogen and giving them off to an off-taker. If this node was a hydrogen node, then because it's at the top of the tree, it would happily accept and mix any of its sub-commodities. So clean hydrogen, sort of dirty hydrogen, and all of them would go off to an off-taker who doesn't care about the emissions intensity. If you made that you created a clean hydrogen subcommodity and made the node that, then if I connected all of them, it would only accept clean hydrogen. So this allows you to really carefully account for, and the outputs, each of these edges reports its flows. So you'd have to do a bit of processing to, in your analysis script to take the outputs and slice them up correctly. But the long and short of it is that you can use these subcommodities to very carefully track what the emissions intensity or types of commodities are being produced, how they're being mixed together. And for things like analysis of the IRA credits and things like that, where you had very careful, you had the 3-pillar rules about when different, let's say, hydrogen was being made and what electricity was being used to make it and where was it coming from. Accounting for all of that was very challenging in old systems, and with macro, it's, I think, very easy. Okay, my last kind of tech slide, and then we'll get into some examples. These are the features we're adding right now. The first one's this graphical interface I'll show you in a second. All the projects that are ongoing, the plan is to publish those models, so there should be standing models of several countries to work with. In some prototypes, we've got AC and DC power flow working. That substantially increases the runtime, particularly AC power flow. You might go from a model that takes a minute to 20 minutes, or that goes from 30 minutes to 10 hours or something, but they can be solved. And along with that, we also have nonlinear technology models where, as an example, electrolyzers for hydrogen production. Currently, the electrolyzers are very expensive, and they generally have a fairly stable price of electricity they're buying from. So they operate at a set point that minimizes their degradation. But most studies are kind of agreeing that as if renewables continue to become more of the price setter, and the electrolyzers become cheaper, then they will be varying their output significantly to optimize their use of prices. And every time they vary their output, their efficiency will move. So that creates a nonlinear kind of element to the system. Yeah?
I have a question. In the point 4 of nonlinear technology models, is there where maybe the data center flexibility technology is going to go?
Yeah, I think anytime. So if you had something like demand response, I think could be linear or nonlinear. But let's say server racks had a nonlinear power utilization. So if they're at 100% load, they require X megawatt hours per unit of output. And if they half that, they become maybe 10% more efficient. Then that would be one of those nonlinear technologies. Because then you could think of the total power usage as the efficiency times the kind of output or the amount of electricity coming in. And linear would just be constant efficiency, and the throughput is varying. And if you were to make the efficiency a function of the throughput, then you have a quadratic one in that case. But some nonlinear technologies are easy, and you barely see an increase in the runtime. Some of them, they do create a bit of a overhead, but I think we're trying to do assessments now to show that that overhead is worth it, because the fidelity you get in the model is much, much improved. Any other questions about that? Or any of the other points? Yeah, we have meetings every 2 weeks with this kind of international group, primarily the US and European group, just because of time issue. And so if there are things that you're working on which you'd like to see added, feel free to reach out to me. You can join. We have the Slack channel where people are putting in questions, or people put them as issues on the GitHub. And if you join the meetings, you can kind of advocate for why something would be useful, or would get help with implementing it yourself. Okay. Oh, sorry, go ahead. Sorry.
Are you modeling hydroelectric power in a, say, special manner, or they are just part of the electric big box?
So reservoir hydro, right now the implementation is very simple. I know there's a group at, I think, Chalmers in Sweden, who did a really impressive, a very impressive nonlinear hydro reservoir model. And so kind of somewhere on the list is the goal to implement that in macro. Right now it's very simple. There's essentially a a storage of electricity, and water comes in at some schedule, and you have to take it out to avoid it overflowing. You can allow some spillover, and you can draw down from that energy storage. And you can put in some constraints to say things like it must be fully charged, sorry, it must be 50% charged January 1st, let's say, to kind of try and put in some of those realistic constraints that the operators will have. But yeah, right now it's a pretty simple model. Yeah.
Is therefore an aggregate representation for a whole area, or not modeling individual cascaded plants?
No, the Chalmers model has that, and so that's, yeah, it has a mixture of reservoirs, must-run, run-of-river elements that are part of it, and it has a whole cascade of through. I can send you that paper. It's a really good. Their approach is very general. I think anyone could do it.
What I'm amazed is that their model can be, let's say, plugged into macro easy, really, because I see that the interface or the let's say, communication protocols in that case would be quite specific.
That has been like, yeah, that's the whole thing of the architecture right from the beginning was, we don't want to guess anything about what your technology looks like or what your commodities look like. And so how could we design all this stuff to, one, allow scaling, but two, just let you come up with your hook together components, those 4 basic components, and it will be happy with it.
Needs to be in Julia, or these other models that can be connected to macro have to be done, can be done in other language?
So I think as it stands now, they have to be done in Julia. It wouldn't be, so with GenX in the past, we did a Python wrapper around like I forget what the Python library is called, but we did a Python wrapper to allow you to run models. I think because this is a bit easier to interface with, maybe it would be also something to write a Python wrapper around there are essentially API functions to let you build things. But actually so as I said, I'll post these slides, and on the documentation, there's lots of workbooks for how to do this. Now I'm going to run through some examples of what it looks like to run these systems. But as I said, please feel free to ask questions as we go, or as we go. Or afterwards. Oh, I am still presenting. Okay. So hopefully. Let me make this all a bit bigger. Okay, so I'm jumping ahead. I'm assuming that I've installed Julia, but there's nothing here. So I've created a little project environment called IAP lecture, which let me raise this up. And I'm just going to show you, if you wanted to, you would open the package manager, and to install macro, you just say, you'd say add macro energy. And it should hopefully not take too long, but Julia will handle this automatically and install it all for you. Oh yeah, no, I'm just going to walk through. I'm just because last time, as I said, unless we have several hours, it's a real slow process to get everyone involved. So I'm going to walk through this a little bit and let people see it.
So I will send the instructions to install Julia.
Yeah, I will send through all these instructions, and as I said, the documentation site walks you through how to like install VS Code, Julia, macro energy, the solvers, and that stuff. Okay, I'm going to skip ahead because sometimes this does hang a little bit. So if I can get control of my screen. So I'm going to jump ahead here to a version where I already installed it just to make sure that we weren't waiting in time too much. And let me clear this. Okay, so here I've installed it, and I've also installed Gurobi, just because we have free academic licenses. But this all works with the Hive solver as well, which is a free solver from the University of Edinburgh. And if I wanted to install some examples, one option, macro has this list examples function. So here are some examples we put online, and we're gradually growing this. But if I wanted to, I could, you can then just download some of these examples. So for example, I might do this 3-zone electricity example, and I want to put it in my examples folder. So it's downloaded, and up here, I now have this 3-zone electricity example. Now I can do this as well, just to show it live, that I'm not just pretending that this is working. But then I have to challenge my spelling. There we go. So multi-stage, and now we have this multi-stage example downloaded. And the main structure of these systems is we did design them for high-performance computers in mind. So at the end of the day, the whole input is a giant JSON file where I have this case, and this case contains an array of these system snapshots and a settings file. And the settings files are pretty simple for this one. It's just saying to use the Bender's algorithm, which I actually don't want it to use the Bender's algorithm to start with. I want to use the monolithic solve. So it's solving it as one big model. And this JSON file has just one system in this case. And I tell it, I have a list of commodities, locations, some system settings, assets, time data, and nodes. And the way we've set this up is that you could just put all of these different things into this systems data directly. And when you're working with a high-performance computer, they much, much, much prefer a few big files to many small files. So if you want to improve or if you want to make the administrators of those systems happy, this is one thing to do. And it also makes it much easier to pass inputs and outputs around. But we've set up the system where there are some reserved keywords. So for example, path is one of them, where it says, if I want these commodities, I haven't put them here directly, you should go look for them at this address. And so if we were to go to system and commodities.json, there's just a simple list here of, there's 3 commodities. And if you wanted to add more commodities, it's as simple as adding, heat, Ruaridh's commodity. All of these things will now become things that you can use and transport and manipulate in the system. And if you wanted to add sub-commodities, let me just grab the syntax directly. You do something like this. So if I wanted to track fossil natural gas versus clean natural gas, I have this little input here where I can say, okay, this is clean natural gas. And now macro will very happily keep track of all these different things. And you can keep chaining them, so you can have this whole tree of sub-commodities that you're keeping track of. And then, if we go back to our systems data file, we go through a list of locations. I'm pretty sure we haven't defined any locations. It's going to happen automatically. And the assets are this list of, again, JSON files. So we have renewables, and there are different ways you can do these inputs. The simplest is for every initial component, for every subcomponent in the asset, you can define different properties and different costs. So for example, in this solar utility-grade solar installation in Massachusetts, we've said this is the fixed cost. It doesn't have any minimum capacity. It's producing electricity as opposed to some sub-commodity of electricity. And again, we have this system where we could just put the availability data directly, but instead we've said, I want you to go and find a time series for me. It's in this CSV file, and I want you to use the column in this header. So if I then follow that along, I can find, okay, here's my Massachusetts solar PV data. And this is convenient, again, for keeping things a little bit readable, but it also means that if you want to work with CSVs for some data, you can. If you want very heterogeneous inputs, let's say because you're doing a nonlinear technology representation where you need lots of different bits of data, it's very easy to encode these things in JSON because it's very, very flexible. But if I had, let's say, 10 solar facilities right next to one another, and they all had the same availability time series, I can just point them all to this same column. And I have transmission, thermal, and storage, and all of these set up in this case. And similarly, I have nodes where I'm saying I have Connecticut natural gas supply, Maine, New England, Massachusetts, same for electricity, and I have a single CO2 sink where they're all being dumped to. Again, I know I'm going through this a little bit quickly because my intention is more to give you a feeling for what can be achieved, not exactly how to do it. But then when you're happy with all that, you run the model. So I've set up a very simple run file saying, run this case that's in this directory, and use Gurobi to do so with these couple settings. I'm just going to turn crossover off so that it runs a little faster. And I'm going to then make sure that I use the electricity one. Electricity 3 zone. Oh. Yeah. And because it's using Gurobi, it's just quickly installing a quick extension for Gurobi. And Julia always takes a second the first time you run things. Oh, what have I done? Oh, I didn't actually use these things. Let me make my life easier, because I haven't actually used these things directly. So it's then going to run. We have a single period model, and while this runs, I'm going to pause for a second. So this is running. It's a pretty small model, so it takes tens of seconds to run, and this is fortunately a fairly quick computer, and it's going to give me a set of results out. And again, I'm not going to go through all of these in detail because the tutorials do a much better job, and it's a lot easier to follow along as you go. But it tells you all the capacities, the different flows on the edges, and you can write post-processing scripts to turn these into nice plots and nice analyses. Any questions about the stuff I've been going through so far? This idea of you essentially define your locations or nodes, you have this assets that you're putting into input data, but this is how you would build that model. Any questions about this? No? Yeah.
What are the results of the expansion decisions made in the...
So in the end, you get these CSV files, and it tells you what were all the different expansion decisions. So we had 3 natural gas resources. It tells us that we had none to start with, so none of them are retired, and we had these installed at the end. And similarly for transmission, these were our line expansions, different renewables constructed.
This capacity is the existing one, and the new is the added...
Sorry, this is kind of the total capacity at the end, and new capacity, retired capacity. There was no existing capacity, so that was dropped.
So this was
Greenfield, yeah, totally flat. And you can slice these in different ways, where there's the costs, kind of the discounted costs for the whole system, undiscounted costs. It tells you how much each of these resources were producing. This is something we're still trying to refine. Right now, most of the people using it are happy to have all the data as a big flood. We're trying to gradually make this more structured so that people can, so it's easier to use out of the box. But yeah, this is what it gives you right now. But if you did have a bigger model and you wanted to rerun this, let's say as using that system where you chop up the model, before, for example, with our Genix system before, that was a very challenging and kind of a time-consuming process. But here, you just essentially tell it to use benders instead. You give some rules about how you want it to be divided up. And I'm using a different run file because in this case, I told it I wanted, you can tell it for the upper level problem, what optimizer and rules do you want to use, and the same for the lower level problem. But I just hit run, and this is now running through the benders iterations to solve this. And so this is a very small problem, not well suited to a distributed approach. But you can see we have iteration 1, we have a lower bound and upper bound and a humongous gap. And gradually, it's just refining these things down. And so I'll leave this to run in the background because it's going to be much slower than the monolithic model. But for example, if you have a couple hundred zone of the whole US, then we find that a system that was unsolvable with a monolithic model, mostly due to memory concerns, memory usage, will solve in a couple hours or maybe 10 hours using the Bender's approach. And as I said, it's just you change one setting, you tell it what optimizer to use for the different levels, and everything is handled under the hood, which is very useful. And we're planning to extend that to myopic, rolling horizon models, and stochastic models, and other things. So I'm going to leave this to run. If you were to want to do a big multi-sector model, nothing is different. And as we talked about, everything is handled the same way. But now, instead of a few nodes for electricity and natural gas, I'm going to have lots and lots of nodes of different commodities telling me the supply of each, the demand of each, and my assets folder will be much, much larger. So I now have all sorts of different assets from natural gas for different commodities. But the process is still the same. Once I've built that all, I tell the system where to find the, where to go. I tell it where to find all the bits of information, and I hit run. Okay. So this is how to run a model. As I said, the workbooks, I think, will make this a lot clearer. If you wanted to start making your own sector model, you could go into the source code here. Well, Bender's case is still running. And you would find the model section and the asset section. And you could create this new asset. So here we have a Beck's electricity. And there's a lot of Julia you have to learn here. And you set some defaults. And then you tell it how to connect all those different assets together. And it's a very recipe-based process, but it still takes a while to learn. So to make that easier, we have started using or creating these graphical interfaces. So I'm just going to hop over here, which isn't going to convert nicely. So let me. OK, so this is our graphical interface for making your own system models. I've hidden them here, but essentially there's this asset maker to create assets, and then we have a system maker that's almost complete to make all the systems yourself. But let's say, I've talked about electrolyzers a few times. So we have the asset, which is this orange box, and I can, if I need space or less, I can make this bigger or smaller. But I'm going to have some source of electricity, a transformation that's going to turn electricity into hydrogen, and a place to put the hydrogen out afterwards. And I'm going to just connect these things like I would, any other drag and drop GUI that you find on the internet. And I'm going to call this my IAP electrolyzer. And we have some summary choices. So I mentioned before that the capacities are done on the edges. So I'm going to say that the capacity is set by the hydrogen resource. So when we're talking about how big this electrolyzer is, I'm going to talk about it in terms of tons or pounds or megawatt hours of hydrogen that it can produce per unit time. And I'm going to give myself some easier to read names here. And I have this transform at the end. And now you can go through and set some defaults. And these can all be changed when you're actually building a model with this asset. But for example, I'm going to say, by default, this should have a capacity constraint. And I could add a ramping constraint or minimum flow or maximum flow constraint, really just to make my life easier later so I'm not having to reconfigure it all the time. And I have this balance constraint here. And so this balance constraint is hopefully reasonable to read. It's essentially telling me what is coming in and out of this transformation. And how should that balance be? What should the coefficients and other rules for that balance be? So in this case, I want to have some kind of efficiency. So I'm going to add conversion, or say efficiency to here. And I'll say it's a number. And by default, it can be 0, just to make it very obvious when I mess up the the inputs. And so now I say, okay, this is actually wrong because I want 1 unit of electricity to make efficiency units of hydrogen. So if this was, let's say, 0.4, then my 1 megawatt hour of hydrogen coming in is 0.4 megawatt hours of, electricity coming in is 4.4 megawatt hours of hydrogen coming out. And if we wanted to, we could make that more complex. We could, let's say there's some fixed element. So we'll say it's 0.1 plus some transform efficiency. And to make the nonlinear systems, we're essentially adding more and more options for these sort of coefficients. If I want to, I can look at the full properties for all of these things and set very complicated defaults. But at the end of the day, it gives me out that code. And so we have an offline version of this that then just automatically throws that into your macro source code. But in our case, this is the browser version. So I'm going to hit copy here, go back to my macro case, and this is still a pain in the neck to do. So I'm looking forward to getting rid of this, but we'll call it IAP electrolyzer.jl. I'm going to just copy paste this in and make sure I remember to name everything nicely. Yeah, which looks okay. Yeah.
Thank you very much. What about in this particular case, if you wanted to add, I don't know, storage of hydrogen that can also impose some constraints to the electrolyzer functioning in terms that you cannot exceed? Would that be possible in this general setting?
I think so. I just made the mistake of resetting of accidentally reloading this. So I'll quickly reconstruct it. So what would be an example? Yeah, if you wanted to do let's say a more complicated system, let's say we also need to account for the water usage and so we have electricity and water coming in, and let's say, we can make some new commodities, let's say gaseous hydrogen, make it whatever color we want, and then we're going to have, actually, I see your point. So we're going to have gaseous hydrogen storage, essentially like a buffer. I've picked a very hard to read color there. And then maybe there's or even like a kind of a liquid hydrogen, liquid hydrogen place. And again, we can have a buffer. So this would be for a facility that's actually pumping. No one delivers gaseous hydrogen really, unless it's used on site. I think most people will use either compressed or liquefied or something like that. So we would then connect this storage to the transformation, and the transformation would turn it into liquid, liquid hydrogen, and perhaps there are losses. So we could this liquid hydrogen. Perhaps we would also have some liquid hydrogen, some gaseous hydrogen from, let's say, off-gassing would come back. So when you liquefy the hydrogen, 10-ish% of it will off-gas and go back. And similarly, we might have some off-gassing from the storage. So you would hook all these things up, and the process would become a little bit laborious because you'd have to start saying, okay, this is my electrolyzer transformation, and then this is my liquefaction transform, and
the capacity of the tanker, of the tank, can be a variable that the model decides as well, or?
Exactly. So it can be just an infinite buffer, and you're more just tracking some buffer, and you don't want to optimize the storage, or you can go through and say, yes, these storage have to have capacity, and you can set, what are the ratios of the storage, input capacity versus storage capacity, are there maximums? So this is where you'd start defining that. And Will it be a long duration storage, so you track it across representative periods? Does it have an age-based retirement if it's on a multi-period model? The big one is the balance constraint, which is by default, we'll just make everything that comes in equal everything that comes out, because it should all be one commodity, but we'll account for some hourly losses. Yes, so you can kind of see how, this is why to your question earlier, could you make more components? We haven't come across anything that needs more than these 4 components. They do become complicated, which is the big reasoning for adding on these, for adding in this graphical interface, because now you get this out and it's essentially, it says here a 500 or 450 line asset definition, but it's all automatic for you. Yeah. And right now it's still a bit of a headache because all of these new commodities we've made, you'll have to manually put those in the inputs. So you have to tell the system, here's this new asset, I've made these new commodities, please keep track of them. But the goal is to, in the offline version, it's still just to have all of these things be automatic. So yeah, and you still have to make those big JSON files for the inputs, but as I said, this is the asset maker tab, and I've hidden, but there's a model maker tab and a model analysis tab that allow you to drag these little locations and drag in an asset and connect them up. So yeah, the goal is that unless you want to make some new constraint, let's say, a new constraint or some new solving method, then you shouldn't ever have to use code. Is the goal. You might have to tolerate lots of UI bugs though, because none of us are front-end engineers, and it's not fun to make. But yeah. Yeah, I've run through a lot. Any other questions about this example? Or, I mean, I was thinking of calling on someone and saying, what is your project? And we would make an asset together for it. But that seems cruel now that I'm here. And now it's almost lunchtime. Yeah. So any questions though that people have? Yeah.
There are communities that you can join to learn and interact and provide feedback.
So the short answer, yes. So we have on the GitHub page, there is the most obvious one is if you come and you have questions, you can put issues in. So some of them are very pointed suggestions, like they wanted an easier way to keep track of how the model was breaking up the time series. Another one was people wanting very verbose outputs for when you're for logging on high performance clusters. But people also had, like this was a conversation we were having with someone 2 weeks ago where they're building this steam cracker system. And we essentially had a discussion about what might be the best way to do that. The kind of extension of this is we have some Slack channels, which people are more than welcome to join. I think right now it's a case of, there's no public link. So if you email me afterwards, we can add you to that. But I think those are the two main ways of contributing or kind of getting feedback and questions. And then the other one is the documentation, which I think if you're interested in this, in using Macro, I'd recommend starting here because it'll walk you through all the details of how to get started with installation, and then has some tutorials for running your first system and what the output should look like, and then building a multi-sector model and how you might gradually increase the complexity of the system. And once you've got those under your hat, you can start using the guides, which are essentially very targeted explanations for how to do a task you might want to as part of your regular work. So the simplest is how do I create a system in the first place? And this isn't really trying to explain why things work. It's more just, here's how to do this discrete task, how to add a new node, for example, how to add a new asset to the system, and it walks you through some examples. If you want the detailed understanding of why things work, we then have the manual, which is still a bit of a work in progress. Some pages are very detailed and give you all the inputs and architecture, reasons why we might have made one architecture decision over another. Whereas others, for example, commodities, I'm pretty sure is totally blank page. So this is still a work in progress, and if people want to point out things that they really need, we'll prioritize that. The other bit is that we have these pictures. There's a library of the assets that kind of come pre-installed, so to speak, and it has these pictures trying to help you understand what they're trying to do. So, for example, I'm pretty sure hydro. Yeah, you can see our hydro reservoir model is very simple. You have some, not even a water resource, an electricity hydro resource that you're storing and can go both ways and things like that. Yeah, I had a couple. I think I'm happy to pause there unless there are more questions. Okay. If not, as I said, hopefully this seems very interesting and useful for your work. The other example, this is very flexible and it's just very convenient for building systems that we, the developers, haven't thought of before. And as I said, if you are looking for things where to start, these tutorials and Get It Started section should have you covered. And if not, please reach out to me and we'll put you in touch with people to walk you through it. Great. All right.